Okay, this is the second hour of Physics 1A for May 17th. All right, so we're going to finish doing this problem that we left class, or we left at the end of the last hour. So we're going to be using energy conservation to find the minimum speed v initial such that the rod makes it over the top. Okay, so let's start plugging in the information we have here. This can be kind of a long equation, so we'll make some space. For the kinetic energy, this system is basically undergoing pure rotation, right? It's basically undergoing pure rotation. The pivot point makes it so that the system is forced to rotate, which means there's not going to be any linear velocity terms in this. That means that for change in kinetic energy, all we have to write down is 1/2 I times omega final squared minus omega initial squared, which in this case is just called omega. We'll put omega initial squared, but we're going to use the symbol omega for it. For the change in potential energy, because there's two different objects here, we can either write out two separate terms for change in potential energy. One of them for the ball, plus another one for the rod. Now for this is where you gotta write like a whole bunch of symbols here. For y final for the rod, it's going to be the y final coordinate of its center of mass plus, not plus, minus, y initial of the center of mass of the rod. It's just a ton. I hate how many subscripts there are written here, but we'll just stop and look at this equation and make sure. Does this equation make sense to everyone? We need to deal with the change in potential energy for the ball and for the rod, basically. Now there is a simpler, there's like a more compact way to write all of this, which would be to simply take the ball and the rod, find the center of mass of the whole system here, which, you know, it's going to be somewhere like right here. And then you could do m total, g, times the change in height of the center of mass. And then you would have just one term. But at the end of the day, you're going to get the same answer, so it doesn't matter how you do it. Just whichever one you prefer, really. Okay, plugging in for I we found in the first part was equal to this, 4/3 n all squared. And that is multiplied by omega final, which we said was 0. Let's go ahead and write in here everything that's 0. So this term is 0. Only one other thing is going to be 0. I think it's going to be the initial position of the ball. Everything else will be non-zero. Okay, so we have 0 minus omega squared, so this is going to be negative omega squared. I'm going to go ahead and just call it omega, because that's what we called it here. 3b naught over 2l, or 4l. Okay, plus. Okay, I don't need to put m ball here. I put that just to be clear about what's going on, but they both have the same mass, which is just m, so mg. Y final for the ball is going to be this, 2l. That's where the ball is at the end. Plus, kind of starting to write down at an angle, and I want to fix that real quick if I can. Plus mg 2l plus the mass of the rod times g. So m for the rod, g, and then the final position of the center of mass of the rod is going to be this, 3l over 2, minus the initial coordinate of the center of mass of the rod was l over 2. And we basically just need to use this equation to find what omega is equal to. No, well, we're going to find v naught. That's going to require one more step, though. Okay, so next thing we do is to take all these negative things and put them on the left-hand side. So 1/2 of 4/3 will be 2/3. Every term has an m in it, so we don't need to write those on the next line. M, and m. So it's 2 over 3 L squared times omega squared. And omega squared is going to be this thing squared, so we'll plug that in. 3 V naught over 4L whole squared. This should be equal to, so we have 2GL, and here we have 3L over 2 minus L over 2, which is going to be just L, right? 3 halves minus 1 half is 1. So we have mg times 2L plus mg times L. I think on the right-hand side, we're going to get this 3mg L, and actually no m because we got rid of that, right? I think it's just going to be 3GL. See if you look at those two terms, if they give you this, if you work out the algebra. Do you get the same thing on the right-hand side over here from these last two terms, 3 times g times L? L squared. Yep, I agree. This is L squared. Thank you so much from there. That should have been L squared right there, in case you didn't see that. In fact, let me just make it a different color so that it's clear that I made an error, in case you're just not noticing what I just did, or you were looking down at the time. That's what I changed. That should be L squared. The right-hand side, is that look good? 3GL? Okay. All right, well, our goal was to find V naught, and we have an equation that only has V naught in it now, right? So we can solve this for V initial. There's enough room to write one more step here. It looks like the L squareds cancel out here. And 2 over 4. So this 3 cancels with this 3. This 2 is going to cancel out with this, and we'll have a 2 left over on the bottom. And nope, that's not true either. Nope, none of those things I just said were true. Whoops. Let's just not skip any steps. All right, let's expand this out. So we have 2 over 3 L squared. The L squareds will cancel out. That part was true. We don't need to worry about those. So 3 squared is 9 V naught squared divided by 4 squared is 16. And this is equal to, the L squared's canceled. And go back. Those are the one things that I can say cancel. So we can go through here and we can say this is going to cancel out with that. And on the right-hand side, we just have 3GL. And so now we can solve for V naught. So we have 2 over 16, which is going to be 1 over 8. So we're going to get this and this cancel. We'll get an 8 down here. This and this are going to cancel with a 3 on the top. And then this 3 is going to cancel out with that 3. And I think we're going to get 8GL. So our answer is going to be V naught is equal to the square root of 8 times G times L. As long as the initial speed is equal to this, then the system should be able to go around. You got the same thing? Great. 8GL. That's good. All right. Anyone have any questions? It's a pretty good problem. Okay. You know, I want to do one other thing. I think... Is your lab manual homework due this week or next week? It's due this week, right? Or was it due last week? It's due tomorrow? Okay. There's a problem on there. Thinking back to when we were talking about momentum, there's an example problem we never did. And I don't know why. I don't know why I didn't do this. I always do this problem. But I've been getting a lot of questions on the lab manual about this. So I think it's definitely worth our while to go back and look at this problem. Because, yeah, I've been getting a lot of questions on it. And, yeah, it's due tomorrow, but you can turn it in all this week, basically. It's just fine. So this is the problem. So this goes back. This is the chapter on linear momentum. And in this chapter, we learned about, conservation of linear momentum, we've used that today. It's a pretty powerful idea. But we also learned this equation, which relates the initial and final velocities of an object with looking at the perpendicular component of the velocity. It looks something like this. If I have two objects, v1 and v2, and I define their initial velocities to be v1 and v2, that if I take the perpendicular component of those velocity vectors and I you take the difference of them, multiply by the coefficient of restitution, which is e, that this should be equal to the velocities after the collision, the same difference, v2 prime minus v1 prime. But again, just the perpendicular component of them. Now there's, I want to say, 3 different problems that are in which you have to deal with this concept on the lab menu homework. And let me just make sure I got that equation right, because sometimes I mess it up. So that's the equation. I can't get them both at the same time unless I push this button. Okay. So yeah, you put these on the initial side, right? Okay, so there's our equation. And note that this says that this equation is only good in the direction perpendicular to the surface of contact. Okay. So in this problem, what we have is we have a ball with an initial speed v initial, and it bounces off of a surface. It has a final speed v prime. It strikes a smooth surface. That's going to imply that it is a frictionless surface at an angle theta with the surface as shown. It says if the coefficient of restitution between the ball and surface is e, find the velocity of the ball after striking the surface. So this is what we're going to try to calculate based on the kind of given information right here. All right. Now, this problem involves a collision of a ball with the earth, basically, with the ground. Okay, so here's the earth. So our 2 objects are going to be the ball. That's going to be object number 1. Sorry, that's supposed to be a 1. Object number 1 is the ball, and object number 2 is the earth. Okay, that's what we're going to use for our 2 equations over here. Because the earth can't possibly move in any way when a ball bounces off of it, in any way that means anything, we're going to say that the velocity of the earth before the collision is going to be 0, and the velocity of the earth after the collision is going to be 0. So v1 and v2 prime are going to be 0. Sorry, v2 and v2 prime will be 0. Okay. And then we'll use the other symbols that are here. So object 1 means that, yeah, we've got these velocities. So our initial velocity vector is v naught, and our final velocity vector is just v prime. Okay. So our goal here is to find what v prime is in terms of the given symbols here. What we know is that the angle made is theta before the collision, and the angle made after the collision is phi. Because momentum problems are always going to be problems that involve coordinate systems. Let's go ahead and drop a coordinate system on here. So that this is going to be our positive x direction, and that is going to be our positive y direction. The y direction is going to be the perpendicular to the surface of contact direction as well, so this is also going to be our perpendicular direction, if you want to call it that. In order to really do anything here, we're going to have to break these velocities up into components, so let's do that. So we'll use this, we'll go green. So this velocity vector is going to start off with a vector that points down like this, and then after hitting the ground, its velocity vector is pointing up like this. And then, what's a good color to use for the, maybe light blue? And then its initial velocity vector in the x direction goes this way. And its final velocity vector in the x direction goes in the same direction. In fact, if I did this right, these 2 vectors should be exactly equal to each other. They're a little bit off, but that's okay. All right, maybe it makes a little sense to move this up to the wider space here so it's easier to see. Okay, so that allows us to break our vectors up into components like that and see what direction they point. So we're going to use both of these equations right here. Okay. We're going to use conservation of x momentum. P initial x direction is equal to P final x direction. And in the y direction, we're going to use that equation right there. Okay, so we'll just copy paste this equation down. So those are our two equations that we're going to use. And by the way, these are also vectors right here. Stop it. There we go. Vector, 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 right? Okay. This perpendicular direction, like I said, is basically for us in this problem going to become the y component of these vectors, because it's the direction that's perpendicular to the surface of contact. This is the surface, so the y direction is that direction. We also know, as I said, that v2 and v2 prime are 0, so this is 0, and that's 0. And what we can do is we can now kind of relabel what these are. In the problem, these are called v initial and v initial prime. So what this equation now says is negative e times negative v naught, that's going to be positive e times v initial y component, is equal to negative v initial prime. Wait, why did I call it v initial prime? That's silly. It's just v prime. Y component. So that's one of our equations. For our x direction equation, the momentum in the x direction is going to be m times v naught. Now we have to multiply. We want the x component of the momentum down here. If this velocity is v naught, what's the x component of that velocity going to be? What would this vector over here be? V naught times what? This angle theta is right here, so it's going to be v naught times cosine theta. Yep. So then our initial velocity in the x direction is going to be m v naught cos theta equals. Be careful about these, the way they're defined, because I know in the problems that you all are doing, I think you're given the other angles, at least a couple of them. So m v naught cos theta. And then this should be equal to p final x, which is going to be m times v prime times cosine phi. This little piece down here is going to be cos phi. For v initial y over here, we can write e times v naught times the sine of theta. We want that component right there. Just realized we can make all this stuff green here, couldn't we? So it's the same color as the... So this is the v naught sine theta right here. And then this side over here is going to be v naught, or is it v naught, v prime sine phi. Now one of these is positive and one of them is negative, right? Which one of these should I make negative? The two green arrows. If I made this positive y direction. Yeah, this one over here. So this is, let's just put it in the definition right here. This is really negative v naught sine theta. Kind of looks like I'm putting the, I think this is a negative sign. So we really need to put a negative sign in there, right? Okay. This is equal to negative v prime y, which is going to be v prime times sine phi. Okay, I think we're good. Now our goal is to find an answer in terms of v prime, or in terms of the initial coordinates, the initial components and stuff. But I think that phi is going to show up on our answer too. So we really just want to isolate v prime from our problem here. So what's the best way to do that? I don't think it really matters. We don't want to eliminate v initial is the main thing. We're going to eliminate it though, right? Oh, okay. So the first thing I thought was we would just divide the equations.
Okay, multiply by -1, then just divide sine of phi to the other side.
Well, we're trying to solve for this variable, right?
Yeah, but wouldn't we want it to make it positive?
Oh yeah, I mean, you absolutely. Yeah, this can be EV not sine theta. No, I agree. That's definitely the next step. But this becomes kind of weird now because everything is in variables, which is it's intentional because you don't know what variables you're going to be given, because like sometimes you're going to be given the initial velocity and these two angles and you find v prime. I think that's what we're going to assume, is that you're given the initial velocity vector and both angles and you want to find v prime. If that's the case, there's nothing wrong with getting rid of one of those numbers. So what I'm going to do is I'm just going to take this equation over here And we'll just divide them. That seems like just as easy as anything to do. So let's divide by this equation, which says v naught cos theta is equal to... No, that's the problem. That gets rid of v prime too, right? Okay, we can't get rid of v prime. Can't do that. So I guess the only other way to do it would be to square and add them. So this equation becomes this. We're going to have v naught cosine theta equals v prime cosine phi. And we're going to square this equation, and we're going to add it to the other equation. So we're going to square both the equations. This is going to get rid of the angle phi, and it'll give us an answer that'll have just v prime in it. So we're going to square them and add them. So we're going to add to this one v naught squared cos squared theta is equal to v prime squared cos squared phi. Add these up. On the left-hand side, we're going to get v naught. So everything is squared. Probably not so obvious the way that I wrote it, but both sides are squared right here. If we square out that first term right there, we're going to get e squared. We're going to get e squared v naught squared sine squared theta plus v naught squared cos squared theta is equal to v prime squared times sine squared phi plus cos squared phi. And then we can solve for v. This is going to go to 1. And yeah. I squared them random because I think any other thing that I do is going to eliminate the thing we're solving for. You know what I mean? Because v prime and v prime show up in both equations in the same way. If I, for example, were to solve for v initial and then plug it in, you can try it yourself. Try another method, Reina. And I think what you're going to see is that every other method you try is going to eliminate v prime, which is fine. That'll give you an answer for how theta and phi are related, and then you could plug them back in. But this just is like probably the fastest way to do it, I think. Does that make sense? Yeah, try the substitution method. Try something else, and I think you're going to see v prime cancels out. Unless I'm crazy. Let me finish this, and I'll do the other method, and I'll show you what I mean, Reina. Okay. Okay, so the answer you end up getting is... Okay, you got it. So I don't necessarily need to do it, I guess. V prime is equal to v naught times the square root of e squared sine squared theta plus cos squared theta. Now, in the problems you're doing, you're not necessarily going to do this part of the problem, because it asks you to do different things, I think. I think it asks you to prove some relationship, right, between the angles. This happens to be the solution for this problem, but the only reason I'm doing this is just to show you how you would do this, basically. To get to this equation here, and this equation is nothing new. We've done problems like this before, but this is the part. Like, we did, I think, one problem like this. I believe the problem we did was... We did two, right? We did two coefficient of restitution problems. So one of them was this first problem right here about the ball, and it was bouncing. We had to figure out how long it takes to stop bouncing. And the other one we did was this one down here, which is just a really simple ball bounces off. You know what the coefficient of restitution is. What we didn't do was the glancing collision. That was my mistake, is I left out doing this part. So I just wanted to go back and show you how you handle things like that, because again, there's like 3 problems on your lab manual homework in which this kind of idea shows up. Okay, and maybe for some of you, maybe you just figured it out on your own. But you know, in case you didn't, then this is kind of how we think about it. Okay, and I think a similar situation happens in those lab manual problems, right, where the ball is either bouncing off the earth. The other problem is there's like some kind of like wedge that's suspended midair, right, and a ball bounces straight down, and then it bounces off of the plane like this. I want to say that's on this homework, right? And you're supposed to figure out something like how far from the edge does it go, right, in this problem. In this problem, you're going to use the surface of the plane is going to be your x direction. So like this is going to be your x direction. and the y direction is going to be perpendicular to the plane like this. This problem's pretty tricky, honestly, but it's a really good problem. Okay, does anyone have any questions? Can you see that if e was equal to 1, that the velocities would be the same as each other, right? It'd be the same. But since e is less than 1, this guarantees that v prime will always be less than v, because the square root here is going to be some number less than 1, basically. All right, so hopefully that was somewhat helpful to you all with those kind of problems. And let's return to the world of angular momentum and look at a problem where the object doesn't bounce or finally look at a problem where the ball doesn't stick to the door. Okay, this one we're actually going to have to draw our own picture. Okay, a 0.2 kilogram ball traveling at 5 meters per second in a direction perpendicular to the plane of an open door. The ball strikes a nail in the door, 0.4 meters from the hinges, and bounces off at 3 meters per second at an angle of 30 degrees with the plane of the door. So this is our picture. We'll start off with a door. Here's our door. It's an open door, and the hinges of the door are here. Probably don't need to make it quite so large, do I? Okay, so there's our door. We have a 0.2 kilogram ball. I'm going to call 0.2 kilograms little m. What's the mass of the door? Is that? Yeah, there it is right there. Okay. So little m is going to be 0.2 kilograms. And in this one, what's going to happen is that ball is going to be moving to the right. And we know what its speed is. We'll call the speed v initial. And say over here that v initial is equal to 5 meters per second. The ball strikes a nail in the door 0.4 meters from the hinges. Now the door is a width of 1 meter. So the ball is actually not at the end right here, but it's instead 0.4 meters from the end. So this would be about half, so it's a little bit above that. And it says that the ball strikes a nail in the door. So somewhere here there's like a nail sticking out, which creates a kind of a vertical surface like this, or a kind of angled surface like this. So this is the nail. And what's going to happen is the ball is going to hit the nail and bounce off down to the left, while the door is then going to swing up. Okay, so this is going to be our before picture. And then our after picture our ball is going to be moving down into the left, I believe. It says the ball strikes a nail in the door 0.4 meters from the hinges, so the hinges are here at the top, and bounces off at 3 meters per second at an angle of 30 degrees with the plane of the door. So the plane of the door would be like this. So 30 degrees with the plane means that it is... I think that means that it's this way. Is that right? So that this smaller angle is 30 degrees? Is that how you all would read that?
Yeah.
Angle of 30 degrees with the plane of the door. So this is a plane. It's a flat plane. The only way I have an angle relative to the plane that's 30 degrees would be like this. So this angle here is 30 degrees. This is the only angle in the problem, actually. So I'm just going to give it a name. That way I don't have to try to write the little degree symbol. So this is 30. Okay, I said I was going to write an angle, and I didn't. We'll call it theta. So theta is going to be equal to 30 degrees. Okay. So that's the direction of our ball after the collision. And that's all we have in this problem, just this and this. There's these two pictures. Okay. Part A. Find the angular momentum of the ball about the hinges before and after the collision. Okay? So we're not using angular momentum conservation. We're just going to find the angular momentum of the ball about the hinges. Okay? All right, so let's write them directly below this right here. what is the angular momentum of just the ball initial going to be?
mr squared.
No, that's the moment of inertia. B final is 3 meters per second. How do I find the moment of inertia of the ball before the collision? So ball traveling in a straight line. In this problem, the hinges are going to represent a pivot, right? There's a pivot right here. So according to our rules, when you have a pivot, you use the pivot as your axis to calculate your moments of inertia, but also to calculate angular momentum. So what would the angular momentum of the ball prior to the collision be here? Yeah, that's right, Miguel. You take the mass of the ball and mass of the ball times its velocity, and then multiply by the distance between the axis of rotation, which is right here. This is our axis of rotation. That's where the hinges are right there. And in this case, that distance, as we said, was 0.4 meters. Ooh, that looks awful. Every time you write a 4. Okay, so 0.4 meters. So we'll multiply this by 0.4 meters. And we can, of course, calculate this because we have the numbers. So little m was 0.2 kilograms. The initial velocity vector had a value of 5 meters per second. And you multiply by 0.4 meters. Anyone have any questions about this? Get the same answer? Everyone get the same answer? Come on, this calculation's really easy. Okay, thank you. All right, moment of inertia of the ball after the collision. So this is a little trickier. Or the angular momentum after the collision. Oh, yeah, the unit's wrong, isn't it? Sorry, that's kilogram meter squared per second. Thank you. Sorry about that. Yeah, kilogram meter squared per second. I'm glad you're paying attention. All right, final angular momentum for the ball. What's that going to be? And again, it's about this axis right here. Remember that if you have an object and it is moving in a straight line relative to an axis, that you're going to use this definition, mvr times the sine of phi, where phi is the angle between the velocity vector and the radius vector, right? You do not need to find the total moment of inertia for this part, no. You don't need to do that, because you can just use this definition, mvr sine phi. That does require that we draw the vector for the r, which would go like this. So that would be the r vector. This is your velocity vector. The other definition is L is equal to r cross p, where p is momentum. They give you the exact same answer either way. So if r goes down like this and the velocity vector goes off like this, what do I write down for the moment of inertia of the ball final? Moment of inertia. Why do I keep saying that? I'm so sorry. It's because I'm looking at the chat and I saw the word moment of inertia and I just said it out loud. What is the final angular momentum of the ball about this axis in this case? Yeah, it's MVR sine 30. That's it, right? I don't know if people are just kind of like sleepy and tired, and I know this lecture is really technical and complicated or whatever, but is this hard? Is it that hard? I don't know. I don't know if it's that hard. I don't think this part was hard, and it seemed like nobody really got this one. Yeah, it's online and stuff like that. Alright, so we've got mass times velocity times r times sine 30. And I have to kind of slow down because if you all aren't following what I'm doing, I don't want to keep going. I don't want to... Does everyone understand how this equation, where this comes from? Does anyone have any questions? Okay. All right. Thank you. All right. So then we can plug the numbers into this one as well. The final angular momentum for the ball is the mass of the ball was 0.2 kilograms. Oh, I made a mistake here. What's wrong about this equation? Something's wrong here, right? Yeah, it should be V final, exactly. So this right here should have been final. V final right there. Hey, let me just pick this. There we go. Okay, this should have been a V final. Sorry about that. So 0.2 times V final, and V final is 3 meters per second. And then R doesn't change because... So, I don't know if this is kind of confusing, but the ball is going along a straight line like this. And obviously the ball is getting farther and farther and farther away from the axis over time. But all we really care about is this initial radius vector right here. That's all we really care about. So R is going to be the same, which is 0.4 meters. And then that is multiplied by sine 30, which is a half. So this one is equal to Does that look right? You all get the same answer? Okay. All right, so that we have the initial angular momentum of the ball, the final angular momentum for the ball. Okay, we've done part A. All of this is part A. Part B says, if the uniform door, and now we get information about the door, has a mass of 12 kilograms and a width of 1 meters. So since we're talking about the width of the door, the length of the door, or the height of the door, would be from the ground up to the top. So this is the width of the door right here, from the top to the bottom. In this case, 1 meter, so 1 meter here. From the hinges down to here. If it starts at rest, we want to find its angular velocity after the collision. Okay, what can I do to calculate that? Calculate its angular velocity after the collision. No, we cannot use initial momentum is equal to final momentum. What's the reason why we can't use that? Why can't we use momentum conservation in this case? Energy hasn't been conserved in any of the problems we've done. In any of the collisions that we've done, energy was not conserved in any of them, so that's not it. It's not because it bounces off. Why can't we use linear momentum conservation? Why can we not do that? Yeah, external forces. This is a pivot. Because there's a pivot, I'm just going to grab this thing again, because I think it always helps to keep looking at this and reminding ourselves what it says so that you're not getting lost in the difference between these problems. So when you have a pivot point, again, there's a large impulse at the pivot, so linear momentum is not conserved. That means that all we can do is this. That's all we can do, conservation of angular momentum pivot. the other piece of this that I left out as I was saying it earlier, the only external force is at the pivot, which means that there's no torque about the pivot, because if there was external torques, then angular momentum wouldn't be conserved. But in this case, angular momentum is conserved about the pivot. But that's all we can do. All we can really say in this problem is that whatever the initial angular momentum of the entire system is, this should be equal to the final angular momentum of the system. Okay? So, the initial angular momentum of the system is going to be the angular momentum of the ball plus the angular momentum of the door. And that's going to be equal to the final angular momentum of the ball plus the final angular momentum of the door. And because the door starts from rest, that means that the initial angular momentum of the door should be equal to what? When it's just hanging there. 0. Okay. That means we only have one unknown in this equation, which is the final angular momentum of the door. And we can see from the calculations we've already done what it's going to be equal to. The angular momentum of the door is basically going to be 0.4 minus 0.12, so it's going to be the difference between these two. So the ball lost some angular momentum. Can you all see that? The ball lost some angular momentum as it went from here to here, as it bounced off the door. But angular momentum has to be conserved, so all of that change in angular momentum has to go somewhere. And it's going to be absorbed by the door, which is going to allow the door to start to swing. And we're going to use that to calculate what the final angular speed of the door is. Okay, so doing that, we have Li ball, which was 0.4. It's unfortunate we don't have a unit for angular momentum. It would be kind of nice. It's like, in this class, we basically start off, we learn about, like, fundamental units and derived units, and then, you know, we only really define a couple derived units in this class. We have the unit for force is newtons, the unit for power is watts, and then we learn about momentum. There's no special unit for momentum. And we learn about angular momentum. There's no special unit for angular momentum. We learn about moment of inertia. No unit for that either. I don't know why we don't use units for I don't know why we didn't come up with our own unit for these things, but it does it's annoying to keep writing all of these units, but it is what it is. So this is equal to, final angular momentum of the ball was 0.12. I think you can write this unit as joule seconds if you want to. That's sometimes what people will write. It's a little shorter, because this is the same thing as a joule times a second. Okay, final angular momentum of the door. For this, we're going to put the moment of inertia for the door multiplied by the final angular speed. So the idea is that now the door is going to be moving with some angular speed that we're going to call omega, and that's going to be what we're going to try to calculate. We're going to calculate what omega is here. Now, in order to do that, we need to know what the moment of inertia of the door is. Now, the door, I don't know if I want to draw this three-dimensionally. I think it's going to end up looking bad, but the door is basically just a rod. In this case, the door basically just equals a rod. And the reason why is because the door has a length of 1 meter, right? So that's going to be the length of the rod is 1 meter. And then the moment of inertia is just going to be the moment of inertia of the rod about one end, which, as we've said a couple times in this class, is going to be 1/3 times the mass of the door. Let's define big M to be the mass of the door. And let's define the width of the door to be L. Then this will be 1/3 ML squared. So the door, even though it has, you'd think like, okay, this is like more like a rod, right? A rod is something that kind of is like long and slender, right? But even something like this, we'll use this as our door right here. So this is our door, right? It's being hit somewhere in the middle, the object's bouncing off, and then it's swinging like this, right? Because it's hinged along one edge right here, like the hinge is basically running straight through like this. It's probably hard to see. This is probably easier to see. It doesn't look like it's much easier to see at all for you all, but the hinge is kind of running along the top. So that means that the way that this object swings is just the same as the way that a rod swings. And you could also consider that the door could just be made up of a bunch of, like, you could take the door and you could break it up into a bunch of little pieces that were rods. Anyway, so it's basically going to have the same mode of inertia of a rod rotating about its end, and that'll allow us to find omega here. So what we'll get is omega is going to be equal to, so 0.4 minus 0.12 will be 0.28, right? And we just need to divide that by I, which is 1 over 3 times big M, which is 12, times L, which is a meter squared. And if we calculate that, oh, it's really easy to do. It's just 0.07 because it's basically 28 over 4. So our final answer is omega is equal to a very tiny number, 0.07, and the units for this automatically become radians per second because that's how we measure omega. And it's a really small number because the door is really big. If you look at it, the mass of the ball that's hitting the door is roughly like, I don't know, what is that, 60 times smaller than the door? So this would be like, you've got an open door, you throw a tennis ball at it, the tennis ball bounces off, and the door just barely starts to swing. And since real doors with real hinges have friction, it's not going to swing for very long, right? It's just going to kind of swing a little bit and probably come to a rest. But this would be its angular speed immediately after the collision. That's what that value would represent. The angular speed of the door right after the collision happens. And then it's probably going to slow down. So there we go. Again, a little bit more complicated problem. Does anyone have any questions? Now, we can take problems like this and we can make them even like more complicated. Like we could ask an additional question on here. The only other question to really ask in this problem would be, what is the force of the pivot during the collision? What's the impulse exerted by the pivot or the force of the pivot on the system? And that's going to be the kind of thing that we're going to be looking at next with these problems here. I think we're going to skip this one. I think we're just going to move into looking at these two right here. But what I'm going to do is I'm going to take these two problems, I'm going to put them down here, and just say something about each one of them, and then we're going to end a little early today. So these are the problems that we're going to do on Wednesday. And again, the other thing for Wednesday that I want to remind you is to read, oops, it's really short. Just read M1. Oops. What's going on? And let me be really clear about what I want you to read, because I don't think I actually want you to just read M1. I want you to read the lesson associated with it. Let me see if I can point to where that is. Okay, so actually what I want you to read is not M1. I'm sorry, that was actually confusing. I want you to read lesson 1. And it is kind of toward the middle. Oh, there's a bunch of ad codes. This is what I want you to read. I'll kind of zoom it up on the screen right here. It's called lesson 1. It's right after F1. So this is the stuff for F1, and then lesson 1 is right after that, right here. Lesson 1. That's actually what I want you to read for next time. So read lesson 1 in the lab manual. Okay, let me get a pen. Okay, read lesson 1 in lab manual. And you don't have to do all the exercises, but it might make sense to start some of them. So the lesson is, I think, 6 pages long. It's about significant figures and error propagation. Okay, I lied. It's a little bit longer than that. And then at the end of it, there's a bunch of problems that involve reading vernier calipers. They involve something about reading micrometers and stuff like that. Try to do some of the exercises. I'm going to have you all turn the exercises in, and I think we'll probably go through some of them in class too, because I know some of them are kind of tricky. Try the practice exercises at the end. You should be able to actually, if you read the lesson, you can do all these exercises. You'll get the most out of Wednesday's class if you've done all of them before you come to class, though. Or 80% of them or something like that. Because then you'll have questions, all that kind of stuff. Regardless, try to read lesson 1. I will talk about some of the theory during class, and then we will kind of go through the practice exercises. I'm going to have you try to just ask questions about the ones that were confusing for you. Just ask me the questions about the ones that, because some of them are definitely confusing. And there's a couple typos in there too, but they aren't major. Anyway, so give that a shot. The questions go on for 3 pages, so don't miss the last page. The last page covers like reading calipers and reading micrometers, which if you took 2A here, you may have done. Okay, so getting back to these 2 problems though. So these are the 2 problems we're also going to do these problems in class. So we'll probably start class, we'll do these 2 problems, and then we're going to do this stuff for the rest of class. So with these 2, these are a little bit different. Let's just read example 11 so you can get an idea for how these are different from the ones we did today. So it says a uniform rod with a mass m and length L is resting on a horizontal frictionless surface. An impulse J is delivered to point D. Right here. So the rod's on a frictionless surface, right? A distance of L/3 below the center of mass as shown. We want to find the velocity of the center of mass and the angular velocity of the center of mass after impulse. So what's different about this problem? The main thing that's different is, in the problems that we did before, there was always like a ball that hit an object, right? In this problem, that's no longer the case. There's just a linear impulse, okay? So an impulse J is delivered at point D. And to solve these type of problems, there is a section here from the same example packet that I have on the thing right here. And that's this. This is how we're going to handle these. I'm going to copy paste this into the thing. Oh, it didn't like that. I didn't want to copy it. I don't know why. Copy, paste. What? Okay, it's not copying it right now, and I don't know why. I'm not going to worry about it. Point is, linear and angular impulse. Single impulse J on a single object. And same kind of deal, there's a no pivot and there's a with a pivot. And there are things that you get out of this, okay? And we're going to use this to solve these 2 problems, okay? And one thing that I think is really cool about this is if any of you have ever played tennis or racquetball, squash, baseball, what else? Softball. If you played any sport in which you hit an object with a bat, a racket, badminton is another example, then you've all heard of this concept of like the sweet spot, right? Have you all heard of that idea? There's like a sweet spot on a bat where you want to hit the ball, or there's a sweet spot on a racket where you want to hit the ball. Do you all know what I'm talking about? Is that really ancient timey language? Does anyone here play any of these sports? Does anyone here play baseball or tennis or anything like this? It's not the middle. Okay, Ange understands what it is. It gets you the perfect hit, exactly. When you hit like a baseball, well, don't worry about where it is, Hudson. We're talking about like what it is, right? Because we're going to calculate where it is. That's what this problem right here is about. It's about finding where it is. But when you hit a ball on the sweet spot of a bat in baseball, you get kind of like the best delivery of the force of your arms into the ball effectively. And you can feel it. It's really noticeable. You really notice the difference when you hit the ball on the sweet spot versus hitting the ball slightly off center. With a tennis racket, it is really, really obvious. If you've ever had a tennis racket and you've hit a tennis ball and the ball hit like really close to where your hand was, like near the bottom of the netting, you don't get as much force out of the ball. The ball kind of almost deadens when it hits the racket, right? So we're going to learn what that is. You guys keep saying in the middle. It's in the middle of it's kind of in the middle of the racket, but it's not exactly. But you're effectively right, I guess, if you want to be kind of a little bit vague about it. Anyway, so we're going to learn what the sweet spot is and how you calculate, how do you find it. And then we'll go into doing this lesson 1 from the lab manual and practice exercise. Yeah. 15 years ago. It's a long time. It's a long time. Okay, so that's all we're going to do for today, because I know that this angular momentum stuff is really complicated, and I can tell that I think you all are a little bit... I think 1 more hour of solving these kind of problems is going to be too much for you all today. So we'll just do it on Wednesday. That means we're going to be here a little bit longer Wednesday, though. So, but I think that's worth it to kind of spread out all this dense material. So that's all for today, and I'll see you all on Wednesday. I am going to stick around after class because there were some specific questions people had about... I don't even remember what they were. I know Hudson had a question. He wanted me to look at a problem, and I feel like there may have been some other questions. So please stick around if you do have questions, and we'll just hold kind of some office hours for the last hour of class here, and that way I can handle just any general questions anyone has about the course, homework, lab manual, whatever you're struggling on. Please stick around and ask questions, because yeah. Anyway, all right. I'll see you all Wednesday. Otherwise, have a nice evening.